Right, good morning, everyone. How did you guys do the homework? Do you have any questions? Go ahead, you have any questions about the homework? All right, you guys so quiet. So yeah, so what I will be doing is, let's see what I left yesterday. And we're gonna work on what we did yesterday. So yesterday we analyzed.
Somebody had questions about the homework.
Excuse me?
Somebody put numbers in the comments.
Yeah, I saw them. Thank you very much. Yeah. Okay. Thank you. So yesterday what we did, we analyzed the following scenario. Okay. Scenario number 1, we had a graph of a function concave up, and scenario number 2, we have the graph of a function which is concave down. Okay. And in this case, we analyzed the second derivative, and we analyzed it and by doing the following. We watched the derivative itself, and we said, you know, what's happening here when it's concave up, the derivative itself is increasing, either by getting less negative or by getting more positive. So if the derivative itself is increasing, its own derivative is positive. And concave down, we analyzed it. We said, okay, the derivative itself seems to be decreasing by getting more negative. And here f double prime is negative. Okay, and then we summarize that by writing, which is absolutely important. If the second derivative is positive, then function is concave up. Second derivative negative, function is concave down. So that's the first time, basically, we see an application of the second derivative. Okay, as far as the graph of the function is concerned. So while the first derivative tells me increasing, decreasing, the second is question of concavity. All right, so I'll use your questions to talk about that. Let me see. '67. So we have the following function: f of x equal. Sorry. Okay. So we have f of x equal e to the x times x minus 3. Okay, that's my function. And the question is, determine the interval on which the functions are concave up or concave down. Okay. Okay, before I do that, there is something important, extremely important, that yesterday I forgot to mention, is the following. Okay, suppose you have a function f, and the function concave up, like that, and it's concave down, and then it's concave up. Okay, there is this point here, this point. At this point, the concavity changes, concave down, concave up. This point has a special name, and it's called the inflection point. So what is the inflection point? The inflection point is the point where the concavity changes. So inflection point inflection point is the point where concavity changes. And we'll try to interpret them later on. Okay, so these are the inflection points. So concave down, concave up, that's the inflection point. Okay. All right, so now, go ahead.
So if the concavity were to not change, like it were all negative, then there would be no inflection point.
Like right here. There's no inflection. Okay, right here,
Okay.
there's no inflection. Exactly. And definitely there is an inflection right there. So it's where the concavity changes. Okay, so we're going to take this problem and we're going to see when it's concave up and concave down. All right, when is it concave up, concave down? It's really a matter of studying the second derivative and asking ourselves when the second derivative is positive and when the second derivative is negative. Okay, so that's really what that's the concavity. So how can we see when this has happened? So it means we have to study the sign of the second derivative. We have to study the sign of the second derivative. So we're going to compute the second derivative. So first I compute f prime. Okay, to compute f prime, I can use the product rule if you want, or I can just distribute because it's such an easy function. I can distribute and then proceed. Actually, I shouldn't have. Okay, this part would require the product. So that's e to the x plus x e to the x minus 3 e to the x. So that's my f prime. Okay, so that's equal to x ex minus 2 ex. Okay, that's f prime. I need to study f double prime, the sign of f double prime. So I want to find out when this is positive. So I compute f double prime. Use the derivative of that. So this is, again, product. So that's e to the x plus x e to the x minus 2 to the x. Okay, so now this is equal to x ex minus ex. So that's my second derivative. Okay, now it's this one that this is the one I would like to know whether it's when this is positive and when this is negative. Okay, the way we figure this out is exactly the same way we figure out when f prime is positive and f prime is negative. So the process is the same. So what do I mean by that? So first we find when f double prime is 0. So it's the same technique. We do that. So this is going to give me equal to 0. I factor out my x. Sorry. I want to factor my e to the x equal to the 0. Okay, so the only way to solve that. So this is going to give me x equal to 1. And e to the x is definitely never 0. All right, so now when is this positive? As I said, the technique we use is exactly what we did for the first derivative. So here we put the sign of f double prime. That's what we care about. So we pick at 1, this is 0. And then we ask ourselves, when is f double prime positive? When is, would there be no, because where is it going to come from? Where is it going to come from? That's e to the x times. So usually if the product is 0, one of the term is 0. One of the term is 0. But in my case, e to the x is never 0. So this piece is never 0. So the only way this product is 0 is for x minus 1 equal to 0. To have x also, I should have that scenario. Then x equal to 0 will be a solution. Okay? But I don't have that. I don't have that. Very good. So now we're going to study the sign of f double prime. So how we do that? Okay, we take to go to the side, and x interval, and be careful. Do not get confused. This is the second derivative this time, f double prime, which is e to the x times x minus 1. It's the second derivative. So don't confuse which one you're studying its sign. So this is 1 here. I need a point. So I need 1 from minus infinity to 1. And from 1 to plus infinity. Okay, from minus infinity to 1, I can pick, for example, 0. From 1 to plus infinity, I can pick it 2. And then I evaluate f double prime. So f double prime here at 0 is e to the 0, which is a 1, times minus 1. So that's negative. And this is e to the 2 minus 1, that's positive. Okay, so what does this mean? It means up to here, the function f is concave down. Here, f is concave up. And this point right here, that's the inflection point. Okay, so let's write those down. So f is concave down for x less than 1. It's concave up for x bigger than 1. And the inflection point is where the concavity changes, is at the point 1, f of 1. That's the inflection point, which is, in our case, 1. My f of x is e to the x times x minus 3. So f of 1 is, I plug in 1 in here, e to the 1, 1 minus 3 minus 2, that's minus 2e. Okay, and that's the inflection point, all right? Okay, now, unfortunately, we don't really know when it's increasing, decreasing. So graphing is not really, I try to graph it, and this is 1 at minus 2e. So the only thing I know that's concave down and it's concave up, something like that. Okay, but it could be like this. So I need increasing, decreasing to be able to have a good grasp of the graph of the function. All right. Okay, so let's do another problem. And which one you guys ask? 71. Okay. Okay, so this is 2x4. That's my function. Plus 8x cubed. Plus 12x squared. Minus x minus 2. And that's my function f of f. Okay, so first let us compute f prime. Okay. So let's see, that's 8x cubed plus 24x squared. So it's the same ideas, nothing really, minus 1. And f double prime is 24, okay, plus 48x minus 24. Okay, again, I have to find when is this positive, when is this negative. That's always my goal, always my goal. Positive, negative. All right, the problem is the same. First, I find when this is what makes it 0. And then in between, it's either positive or negative. It cannot change sign. So I find when it is 0. So this is going to give me 24x squared equal to 0. Now, obviously, those problems are made up, so you can basically solve them. And obviously, I can divide by 24 across. So divide by 24 or factor it out. You can factor out 24 immediately. And you will be left with 2x and minus 1. Okay. And this will give me 24 x minus 1. No. Okay. So is this factorable easily? No way. B squared, which is 4. Can we factor this one? Can we factor it? Can we factor this one by looking at it? What do you think? No. Yeah. No. I was hoping this would. All right. Very well. Okay. So we have to use the quadratic formula, which is minus 2 plus or minus the square root of b squared, which is a 4 minus 8 minus 4ac plus 8 over 2. It means, so if we do the math, it means minus 1 plus or minus, sorry. So it's minus 2 plus or minus the square root of 8. That's 4 times 2. So that's going to give me 2 square root of 2 over 2. So we basically divide by 2 across. I will get minus 1 plus or minus the square root of 2. So we have 2 solution, minus 1 plus root 2 and minus 1 minus root 2. Okay. All right. No, we cannot factor it. I mean, there is no way, by looking at it, there is no way I can find 2 numbers. When you multiply them, you're going to get 1, unless those number is like a half or something. Anyway, no, minus 1 plus root 2. So this is always, you put those in an increasing order. Okay, this way. Very good. So now we just study the sign. The sign and the sign. X. So we have a bunch of interval, minus infinity, minus 1 minus root 2, minus 1 minus root 2. Those are my interval, and minus 1 plus root 2 to infinity. And this is, be careful, that's the second derivative. It means this is 24 times x squared plus 2x minus 1. All right, so the rest is actually now simple. I have to pick a value in here. Now, square root of 2 is 1.4. So I will have minus 1 minus 1.4, right? Let's give me minus, so minus 3 will do, I think. And this will give me 24 times 9. 9 minus 6 minus 1, right? So that's a 9. And that's a minus 6, that's positive. And so that's going to be positive. Right here, I can put a 0. I think 0 is in between. And f double prime at 0 is 24 times minus 1, negative. So that's going to give me positive, negative, and finally, I can pick here 3. and I can compute f double prime at 3, and we will get a positive number. You guys plug it in. Okay, that's it. So that's it. So now what we have is, we have everything we need. So my function is concave up for x less than -1 minus root 2, bigger than -1. And it's concave down for x between those. Okay, and inflection, they occur at the point -1 minus root 2, f at -1 minus root 2, and we're not going to compute them, it's a bit messy, and -1 plus root 2, f at -1 plus root 2. Okay, so that's really what it is. Okay, so it's really basically we're doing the same thing over and over. All right. Questions? Okay. Now we would like, do a problem where we can like sketch things. So we can start putting, those problems together. So we see how they affect on the graph. So let me ask you first something. Very basic. So sketch the graph, and then we do a problem where would like to sketch, so we know how this affecting the graph. So let's sketch the graph of a function that satisfies the following. So very quickly on a piece of paper, f prime positive and f double prime positive for all x. Quickly, all of you. So now we know how to find them algebraically. Now we're going to use them to sketch. Okay, did you guys do it? So how the graph's going to look like? Anybody just mute and tell me what to do. Come on, guys. Okay. F prime positive, F increasing. F double prime positive, F concave up. Okay, that's how we're going to start slowly. So F increasing, F concave up, F increasing, increase, concave up, increase, concave up. Okay, so another one. You want F prime positive, F double prime negative for all x. Positive, negative. What's the effect? Increasing, concave down. Increasing, concave down. Okay, so we should be able to graph, extremely well. And let us see another example. Suppose I ask you f prime is negative for all x. And f double prime is positive for x less than 1. And negative for x bigger than 1. Okay. So I give you a minute or so for you guys to do it in front of you. Okay, one of the things we're going to build usually the following habit when we're going to graph more and more is those number line. So f prime negative for all x. So here I can write the sign of f prime. So f prime is negative. Okay, and this will give me the sign of f double prime. So this tell me up to 0, f double prime is positive. So up to 1, and it's negative after that. Okay, so we're going to start building slowly this kind of idea. And what's going to help us is start analyzing how to graph functions. So how would I do that? So suppose I say, okay, according to this, up to 1, my function is decreasing, concave up, decreasing, concave up. So when I'm going to start sketching, I'm going to be able to sketch while analyzing this. So decreasing, so up to 1, that's my 1. I don't know what's the value of my function, but I know it's going to decrease, concave up. So it's going to decrease, concave up to 1. And then it's going to keep decreasing, but concave down. It's going to keep decreasing, but concave down. So we definitely have an inflection point right here. Okay, so that's my inflection point. All right. Okay, next section, we're actually going to spend most of our time is sketching those graphs. So we're going to study the whole functions as a whole. So we're going to study when it's increasing, decreasing, and finally we're going to sketch it, which is, so we're going to put the whole thing together. All right. Now I'm going to talk about something, the second derivative test. All right. So yesterday, we talked about something called the first derivative test. And let us see what the first derivative test tells me. The first derivative test is about if you have a local mean or a local mark, if you have a critical point, and it means a point where the derivative is 0. And you want to know whether this critical point is a local max and a local mean. So you study the derivative, as simple as that. So this is a critical point, C critical point. Then we study the derivative. We take f prime, the sign of it, near the point. So that's C. And we start asking ourselves, is the derivative moving negative to positive? Negative to positive, then okay, we have a local mean. And it's moving, we have a local max, and so on and so on, so forth. So this we call that the first derivative test. First derivative test, because it uses the first derivative. It uses the first derivative. Now there is another test called the second derivative test, which is also help us figure out whether a critical point is a local max or a local mean. So you have a critical point and you want to ask yourself, okay, is the function doing this here or the function doing that? What's the function doing? Or whatever, what's the function doing? So the second derivative test. Okay, all right, let's see what does it say. It tells me the following. Suppose C is a critical point. Remember, critical point is when the derivative is 0. Let C be a critical point. Means the derivative is 0 or the derivative does not exist. Okay? All right, then if you take this critical point, it means you found it and you evaluate it. That's sometimes very confusing. So you evaluate the second derivative at this critical point. Okay? You evaluate the second derivative at this critical point. And you realize that you get a positive number. So what can we say about the critical point? Is it a local max? Is it a local mean? Or neither? analyze the point a little bit. Think about it. Okay, think about what does this mean? So if the derivative is second derivative 0, positive, what does this mean? Come on. Local mean. I don't quite understand the last comment. Yeah, I don't understand this one. All right, let's see what's this. Okay, so this is a point C. If the second derivative is positive right here, it means that the function is concave up right there. That's really what does it tell me. Okay, so it's a critical point. It's a critical point. It means the derivative is 0. Okay, that's the derivative is 0. So the question is, okay, the derivative is 0, but what's the second derivative tells me? The second derivative tells me that near this point, the function is concave up. That's really what the picture is. Since concave up near this point, it means that's a local minimum. So if f double prime at C is positive, then f has a local minimum at the point C. Okay, so that's how we analyze this. Now, if the second derivative is negative, the second derivative negative, then means again, right here, we have a horizontal tangent, and if it's negative, it means it's concave down right there. Then f has a local mean. Sorry, a local max. Has a local max. Okay, and finally, if the second derivative happened to be 0 at this point, and that's problematic. If the second derivative take a value 0, and then we actually don't know what goes on at this point. It could be a local max, local mean, or neither. So then, and then I'm going to ask you to give me example where to show me that all cases can occur. Then f can have a local max, so actually a local max, local mean, or neither. Or actually what we're going to say is the test is inconclusive. And what does it mean the test is inconclusive? The test is inconclusive. We need to use the first derivative test. Okay, inconclusive, it means the test cannot get me any result. That's what inconclusive means. It means at this stage, it could be a local max, local mean, or neither. All right, so before we start practicing this, I need to ask you the following questions. Okay, give me, I think you can do it. Give me an example of a function. You will give me a function such that the function has a critical point at 0. Let's pick 0. The second derivative is 0 at 0, and the function has a local max. Okay, so we're going to say why if f double prime at C is 0, the test is inconclusive. So I want you to give me an example of a function such that f prime at 0 is 0, f double prime at 0 is 0, and the function has a local max. Go on. that are too quiet today. Example of a function that has at 0, the derivative is 0 at 0, the second derivative is 0, and the function have a local maximum or local mean. I don't care. Just give me one of them.
Okay. So if you use negative x to the fourth, I believe that'll do.
I love that. Yeah. Okay. Let's use f of x equal negative x to the 4. Okay. Watch this function. First f prime minus 4x cubed, f double prime minus 12x squared, f prime at 0 is 0, f double prime at 0 is 0. Okay, so it's a critical point, but this function has right here a local max. Okay, so when the second, now of course it doesn't take that much. If I take f of x equal x to the 4, we're going to have the same thing, local max. It's going to have a local mean. So x to the 4 will have all those properties, but have local max. So if the second derivative is 0, as you realize, we have a lot of different scenarios. And who can give me an example where the second derivative is 0, the first derivative is 0 at 0, and the function doesn't have neither a max nor a mean at 0. So it's a critical point. It's a critical point, but there is neither max nor mean.
I have a question.
What?
I have a question.
Yes, please.
When it says f prime of 0 equals 0 and f double prime of 0 equals 0, how'd you get those?
I plugged in 0 in it.
Oh, okay.
Okay, yeah. Who can give me an example of a function? Again, I want that have all those properties, but I don't want it to have neither a max nor a mean. X cubed, absolutely. X to the power 3. X to the power 3 will do it for us. X to the power 3 will do it for us. It will have all this property, but it's actually going to have neither. No max and no mean. So this tells me that if the second derivative at 0, the test is inconclusive. So now we're going to practice the second derivative test. Okay, so let's do that. Let me take the following function. Let f of x be equal to f of x equal x cubed minus 3x. Okay, and the question is first find the critical point. Okay, let's find the critical point here. Critical point, it means when the derivative is equal to 0. That's the critical point. So f prime equal 3x squared minus 3. So this is equal to 0. Mean 3x squared minus 3 equal to 0. That's a simple one. 3x squared equal to 3. X squared equal to 1 means x equal plus or minus 1. Okay, so that's the critical point. Now question number 2. For each critical point, decide if it's a local max or local mean by using the second derivative test. So use the second derivative test. To decide if it's a local max or local mean, or if it's inconclusive. Okay, so I want you to use the second derivative test. So I wanted to use this time the second derivative test to decide this. Okay, how do we use the second derivative test? The second derivative test tells me that you have to take the function, and you have to evaluate the second derivative at the critical point. You evaluate the second derivative at the critical point. So first I'm going to compute the second derivative. Okay. What's the second derivative? The first derivative, 3x squared minus 3. So the second derivative is 6x. That's 6x. Okay. Now, the second derivative tells me you evaluate. It says you evaluate means you find the value of the second derivative at the critical point. Okay, so my critical point are plus or minus 1. And you need to find the value of the second derivative at that. Okay, this is going to be equal to 6 times 1 is equal to 6, which is positive. Okay, so it means at 1, that's 1, we have a horizontal tangent, and the second derivative is positive. It means it's concave up at this stage. So that tells me that f is concave, f is concave up. It means f has a local maximum. Okay, so that's how we use the second derivative test. All right. Now, the other point. Now I have to evaluate it at minus 1. Okay, so at minus 1, you get 6 times minus 1, which is equal minus 6. Minus 6 is definitely negative, and usually I don't want my student to memorize. I just want them to really understand what's really happening. So it's negative, it means that's what's going on. So right there, we have a horizontal tangent, but the function is concave down. So that's negative, so it means that f has local max. Okay, so sometimes the second derivative test is actually easier, than the first derivative test. You don't have to study the sign. The first derivative test, you have to study the sign of the first derivative. And this one you don't, you just evaluate. The only problem with this test is the following, is that if you get, did I mess up? I'm sorry. So I drew the picture and I wrote nonsense. Okay, thank you. All right. So the benefit of this test that it's easy. You just find the second derivative and plug the value. That's really what it is. The first derivative, you have really to study the sign. The problem with this one, that if you get the critical point and you find the second derivative and you get a 0, and then you have a problem. Because if you get a 0, it means you cannot, this test is inconclusive. Okay. All right. Now I'm going to talk a little bit about inflection point. Okay. All right. So we're going to talk a little bit about inflection point. First, their meaning. So inflection point in a clear way. What are inflection points? So inflection points are, as I said, what did I say? The definition. Inflection points, those are important, very important. Inflection points are points where the concavity changes. Where the concavity of the function changes. Okay, first let us see what do they mean? I mean, if a function changes concavity at a point, what does this mean? And then let me take the following. Suppose I give you the graph of, I tell you this is a population, and then the population behaves like this. So it is concave up, and then it's concave down. Okay, so right here, that's my inflection point. Okay, so what does it mean? What happened at this point? That's what happened at this point. Right before that, so this is my inflection point, that's my P. Okay, what happened here? Prior to P up to here, the function is moving at a faster rate. And then at this point, it keeps increasing, but it starts increasing at a slower and slower rate. So inflection point are those points where exactly the functions, the rate at which the function changes, something happened to it. So it's like when the function changed from moving rapidly, at some point, that's what inflection point, the function keep increasing, but it's the rate at which it is increasing, which is going down and down and down. So that's really the importance of the inflection point. And that's why sometimes in real life we use the inflection point. Okay, people say we are at an inflection point, which they mean that you are moving very fast, but not at an inflection point. It means we're starting moving at a slower and a slower pace. Okay. Now, so that's in what's the meaning of it. Now, question number 2 is, where do they occur, inflection point? It means if this is an inflection point, what can you say about the second derivative at the inflection point? The inflection point occur when what happened with the second derivative? Right, so the second derivative from, every word you guys wrote is perfect. So prior to that, let me take this example. Up to P, here the second derivative is positive here, and the second derivative is negative. Okay? So at the inflection point, what can we say about the second derivative? At the inflection point. Yeah, the second derivative goes from positive to negative. Yes. But what's the value of the second derivative at the inflection point? What do you think is the value of the second derivative? The value of the second derivative is equal to 0. Okay, so inflection point occur when the second derivative is equal to 0. Okay, so this is really, this is where they occur. So they are basically the critical point of f prime itself. And that's very important. They are very important because it actually tells me where the rate is changing. The rate, not the function. The rate is changing. It moves from increase to decrease, or we can have a different scenario. The population can at the beginning be growing slower, slow. That's very possible. And then the population takes off. And that's right here is my inflection point. So right here at the beginning is moving at a slower and slower rate, and then at a faster and a faster and a faster rate. That's right there, my inflection point. So it's really what it happened when it's the rate itself is moving from being fast, slow to fast, fast to slow. That's really the inflection point for us. And they usually occur when the second derivative equal to 0. And to find them, basically to find the inflection point, we have to study the sign of the second derivative and figure out what's really going on. Okay, right? Do you guys have any questions? All right, so that's it for today. I will put up the homework right now. Bye-bye for now.